Beyond the model, you need a pseudocode notation for formalizing algorithms. So let's start with our traditional sequential pseudocode notation, and let's make the following changes. First, we'll write our algorithms assuming a single program, multiple data style. HPC nerds refer to this as SPMD or SPMD style. The way SPMD works is as follows. First, you'll write some pseudocode algorithm. Then you'll imagine running that algorithm on some cluster, and you'll assume that that pseudocode is replicated on all the nodes. We'll call every running copy a process. Each process runs independently and asynchronously from the others in the absence of barriers or any other kind of explicit synchronization. Now, to distinguish the copies from one another, we'll assume that the pseudocode algorithm has access to two global variables, one called rank and one called p. Since the memories are private, these variables are private to each running process. Rank will be the ID of the running process, and it'll be unique. P will be the number of processes. Now, for the moment, the concept of a process and the concept of a node are basically interchangeable. But in practice, a process virtualizes the concept of a node. That means you might have more than one process assigned to a node if, for example, you're running on a multi-socket, multi-core system. Now, to see how this works, suppose that this pseudocode algorithm contains a line of code which reads as follows. So when all the processes run, they'll all print statements of the following form. I am 0 out of 5, I'm 1 out of 5, and so on. They each print their own rank and the total. Here's the second change to sequential pseudocode. I will give you a primitive which performs an asynchronous send. Think of it as an API call that looks like this. Now it has two arguments. One is a buffer of size n, and the second is a destination rank, basically the rank of the process that's supposed to receive this message. Now, an important and subtle point about send async is what does it mean when it returns? When it returns, it does not mean that the buffer has been sent. It just means that a send is registered with the system. So in particular, until you know what's happened, you should not modify buff. To find out what happened, send async will return a handle. And you can do some testing on the handle. Now, for this send to eventually complete, the destination rank has to post an asynchronous receive. The signature looks the same. It names a buffer of some size, and it names a source rank, the source being the sender. Just like send async, when receive async returns, it does not mean the data is available. Rather, receive async will return a handle, and you should do some testing on the handle. This business about handles brings us to the final primitive, which is called wait. In particular, wait is a blocking operation that takes one or more handles as arguments. Now, wait will pause until the corresponding operations complete. Now, there's also a special form of wait called a wait all, abbreviated here by wait with an asterisk. This is a shorthand that says wait for all outstanding sends and receives, so that we don't have to track and check all the handles all the time.